This is section 2 of chapter 3, and it's called Measures of Variation. Now think of the word in vocabulary, variation, is change. It's a change of something. Variation, what is changing? Well, in statistics, we talk about this variation as a measure of the distance between each data value to the arithmetic So this variation can give us a clue of the spread by the value of it. And now we introduce something else, that the square root of the variance is the standard deviation for a statistic group, a sample, or population. So we're going to do all of this as we approach this material. The most important section in this study of variation of data is using range, standard deviation, and variance. So we have 3 topics in this guy. And range is easy because that's the spread. And standard deviation is the square root of the variance. And the variance is the measure of the data points to what we think the mean is for each, for the data set. So let's get involved with this. It sounds difficult, but it's not. As we have learned from statistics, is a study of the data to assess, understand, and interpret. So the focus is why the need for these values. And that's a clue there. Why do we need this? Well, in mathematics, we're always looking for opportunities to evaluate the strength of the sample from various measures. In 3.1, we looked at the 5-number summary, the mean, median, and mode, rather. We haven't really gotten to the 5-number summary, but we used the 5-number summary to figure out the central tendencies of data. And we didn't get far enough to evaluate if the mean equals the median and equals the mode, because this scenario is the perfect setup. Okay, now we're getting to that after this one, because in between getting these 3 items, we have to know then the measure of this mean against all the mathematics to get the standard deviation. So we can also use StatCrunch to assist in doing the homework easily, as well as a TI 83 or 84 for time assessment. Now what we're going to do is I picked problems that you could stick in your calculator, or you can hit the keys on StatCrunch. It's a very easy program, and you should be able to succeed in understanding the headings, because the headings under data state whatever you want, variance and means and all that. So it's pretty easy. So I don't go through it though, but you are welcome to use it. So we're going to take the basic concepts of variation first. And it's a round-off rule for measure of variation. When rounding, the value of the measure of the variation carry one more decimal place than is present in the original data. So this is a rounding rule. So if a whole number, then one decimal. If two decimals are in the data, then three decimals. That's all it means because of the accuracy of what we're trying to achieve. So here we have an example. And in this example is the study of time. It is a dot plot of waiting times in seconds with single and multiple lines. Single lines mean that you're in a row and then wait for the next available. And we can see something very interesting. The single line has a center of activity, of change, with very little variation. Look how close there is. Now, the multi-line means that, think of a bank, and everybody can choose whichever teller they want, and they wait. And look at the span. Now, another example is when you pick your line at HEB to be checked out, and the person in front all of a sudden has coupons, and the cashier says, wait, they don't, do you have this? Did you buy this? Oh, I'm sorry, it's the wrong size. Or, oh, I'm sorry, it's the wrong, uh, you know how they always have different tastes on those, on some of the products, and it didn't fit the coupon. And it angers the customer. So the multi-line means, boy, if you get unlucky, you get that line, even though it's shorter than another line. But the problem is what happened with the poor customer. So we're going to talk about the ranges. Well, what is a range? It is the highest data minus the lowest. And what this gives us is a span of, or spread, spread of the data. How wide it is, how short it is, and we can tell from the single line that the span is not much there. But here, oh my goodness, it goes from 85 to 125 seconds. So that's what they're asking us. What are the ranges of wait times in seconds of the dot plots? So the single line. So we can see that the very center is 100. So I can say 100 is right here. So 99, 98. 98 is the low. And the high is 1, 101, 102, 103. So I do the math on this guy, and I get 5. Which is 5. Oh, is it 102? Oh my gosh, can't count. It's 102. Sorry about that. And it is 4. So the span is 4 seconds for all the customers that they gauged from using this single line. Well, a multi-line, the low is 84 and the high is 125. And we get, um, it looks a little bit like 41, right? Yes. So here, the range, and so what does it tell us? The customer has shorter wait times in the single line than the multi-line. So the customer is getting service quicker, and that always gets a happier outcome. So that's what range is. And here's the formula from the book. It says, and it's elegant because what I gave you was a generality. The range of a set of data values is the difference between the maximum data and the minimum data. So differences always mean subtraction. All right. So now we're going to talk about standard deviation. Standard deviation. And the standard deviation is one of the focal points of the statistical analysis. It is the uniform value calculated using the data value minus the mean divided by the numbers and quantity. And if it's a sample, it's n minus 1. All right. But we're going to do everything by calculator. You just need to know it's what we measure in between each of the, what we did on the last part of 3.1 was the bell curve. And we said 0 is the mean, and then it was 1, 2, and 3 to the right, and then -1, -2, and -2, so on. So it is that, but using actual values instead of I'm not good at drawing. So this would be 0 because that is our mean. Or it could be in a population, but it's a mean. And instead of having 1 standard deviation and 2 standard deviations and 3 standard deviations, and over here we'd have a negative standard deviation, a -2 standard deviation, we're going to have actual x bar plus the value of the standard deviation for the first one. So that's what we mean. And we're bringing in, and I'm saying it a lot, we're discussing the differences between a sample standard deviation that uses n minus 1 and a population standard deviation that's divided by kappan. And that's what we have over here is that formula for a standard deviation. And I forgot to put my square root over this mess. But here it is in the form. And we'll use a calculator. But what I teach you is recognition. Because it describes what it wants. It says the sum of the changes of the data minus the mean squared divided by n minus 1 less than the sample size, because this is a sample standard deviation. And of course they have an alternate, and all this is depending on what kind of calculator you have. This is a much easier form if I were doing it by hand. We will start with using the calculator notes from a previous section on the 5-number summary. So you have this. And I'll go through it as I do the lesson, but I'm not going to insert it. You definitely have had it several times written in your key properties of standard deviation. It what? Measures how much data values deviate. Deviate means change from the mean. They are equal values, which is what I said, plus or minus from the average. Standard deviation is never negative. So that's important. Standard deviation, when you do a computation, is never negative. And of course, we're doing calculators, so we're good. The larger the standard deviation, now this is important. The larger the standard deviation, the greater amount of variation. So we saw that with our time. You saw that the range for the ones that were centralized when we did it was 4. And when we did the multi, it was 41 seconds. So that consideration goes with that particular statement. The standard deviation can increase, decrease with the addition of outliers. Okay, remember what an outlier is. The outlier affects the mean. So if we have a small one, say we have a small data, then it pulls the mean. So consider this. So I have this. All right, and it's probably skewed to the left. I have a number of 3. And normally the mean is in the middle of the hump. Well, it's not. It's now this part, because it pulls it to where it is. Well, if it's a large value, well, then we're skewed where? To the right. And now the big number, and say this is like that 2,000 we had in the last section, it pulled it over here. Well, the mean should have been right about here, because if we wouldn't have had that, it would have been a bell curve. Now it's over here. It shifts it to where the big number goes. So that's what it means, that the standard deviation can increase, decrease with the addition of outliers. And sometimes in our real world, we drop them. We drop them because they're anomalies or input errors. The standard deviation is change per unit described of data, feet, inches, time, etc. It has a name to it. That's what it does. The sample standard deviation S is a biased estimator of the population standard deviation theta. This implies the sample standard deviation S do not center around the value of theta. So that's what happens in your study. You take samples and it should reflect a similarity to the population information. All right. So this part is important and you must put it in your notes. We will see this repeatedly. We're always testing the structure of the mathematics to inform and to alert of changes. All right. So again, we have this little ruler type arrows. It says the rule of thumb to help understand and interpret standard deviation. General understanding is that 95% of the sample should lie within 2 standard deviations, and we learned that in this last section of the mean. So 95 is here. So that means 5% shared should equal 5%. Now we're going to get to that specifically later on in the course. But right now, you need to know the bulk of this information. 5% is usually the standard gauge of significantly low or significantly high. So we're talking this particular area here on that bell curve. So the range rule of thumb for identifying significant values, that's why I said you have to have this in your notes. And if you write it, you own it. So it's very important to me. It makes the other parts easier. Significantly low values are mu, that's for population mean, minus twice the standard deviation, 2 deltas or lower. So that gives you the movement of that from the mean of where the data lies. And I remember, if it's significantly high, it's kind of skewed to the right. If it's significantly low, it's skewed to the left. So that's the low. So they're talking about that one. And then significantly high values are mu plus 2 thetas for higher. Values not significant are between those 2 values. All right, and that's from page 101 in the textbook. For samples, a quick and dirty standard deviation is range divided by 4, but this is only if mean is unknown. So now we're getting to the big one. That's the one we started with, and that was variance. Variance. The variance of a set of values is the measure of variation equal to the square of the standard deviation. Okay, yeah, you remember that was that x minus x, well, this was mu, so let me use the nomenclature they're using. Divided by n, what was it, n squared, let me look again. Oh, it's on the bottom, hold on, sorry. I have it now. Anyway, it's the square of this is the variance. And in our calculator, we find, so if I take the square root of this, then the standard deviation is the square root of the variance. This is the numeric movement. This is the measure. Between data and mean. So you can see the connection of all the mathematics now. I don't want to put a wrong sample in there. And this is the other part that's interesting. And it is one of the questions that you have. And you need to look at it. And a small s is a sample standard deviation. A lower case s squared means I have s to the 2 is the sample variance. All right. Well, then we have the delta is the population standard deviation. And of course, delta squared is the variance for the population. There's a question on all of that in your homework so that you can get familiar. Now, what I have typed in here is the fact that I don't want you to calculate manually the variance. What I want you to do is to use 4 decimal places on a standard deviation and square it. Then round to the place that they say, and it will come out correct. Okay, 4 decimal places is what you square of the standard deviation. So if I have if I have S for theta, I want you to use 4 decimals and then square it to get variance. Variance is S squared or standard deviation squared. The key properties of variance. I typed these up so that you could read them for sure. And they are, unit notations are in squared units. Variance can increase with the inclusion of outliers. It is not resistant. If it is resistant, that means that we have so much data it doesn't affect it. Variance is never negative because it is squared. All that information is squared. Variance, like the standard deviation, the sample variance, S squared, is an unbiased estimator of the population variance, or should be. So it is a test. To support the claim of the population variance. So that's what you, okay, now I'm going to stop right there. And I've talked for about 30 minutes. This is very meaty information, and I hope I've made it clear. We'll do examples, and I can promise you, you should have no issues understanding all of the definitions that I've thrown at you. Don't panic. It's not difficult. We're going to be using the calculator. Thank you for listening.